Alright, the purpose of today's video is to apply what we learned about graphing absolute value functions to solving absolute value equations. So basically the graphing skills that we had are going to make it, I think, ridiculously easy to understand the algebra related to solving absolute value equations. The algebra itself is relatively simple, but, well anyway, let's take a look. I'm going to graph the left-hand side and the right-hand side as if they are both separate functions. On the right-hand side, we could see y equals 5 minus 2x. So to graph that one, we graph a linear function with a y-intercept of 5, 0, 5, and slope of 2. So we should be at 1, 3, and 2, 1, and so forth. So I produce that line. Now we have the left-hand side, which represents an absolute value function that's shifted to the right 1. Slopes are going to be plus or minus 1. So those are three solutions right off the bat, the vertex and the 2 points in the opposite directions. So very quickly then I'm going to label each ray, keeping in mind here, it looks like I had a little mislabeling here. Give me 1 second. We're going to make sure that this negative shows up. There. Good. So when I look at the graph, I can see that there's only one actual solution. When we do our algebra, we're supposed to break the absolute value up into two separate equations. The good news for us is because we have a graphical representation, we know that of the two equations, one of them is going to produce a truth, and the other one is going to produce lies. And so it's our job to discern. So here are the two equations that should emerge by getting rid of the absolute value. In the first case, we write an equation without absolute values at all and then just solve algebraically. In the other case, we take whatever's inside the absolute value and take their opposites, so the opposite of x and the opposite of negative 1, and set that equal to 5 minus 2x as well. Notice the 5 minus 2x is unchanged. Graphically, we're talking about the whole line. Now, making an observation, since there is only one intersection, that is the intersection of the blue line with the increasing portion of the absolute value. In other words, when x minus 1 is equal to 5 minus 2x, we will have this intersection that appears at x equals 2. On the other hand, we have this equation with the decreasing line and the blue line, and that's going to produce a lie. So what we can do is actually identify, based on the graph, that the second equation will produce lies, and just go about the business of solving the first equation. It shows up with x equals 2, which is absolutely right, and in case there's any doubters out there, we can verify that indeed we have found the correct solution if we have the time. So that's the whole process. We have nothing really new here to learn because we've learned how to take absolute values and break them up into separate entities, and we've learned how to graph absolute values, and we've learned how to graph lines. So all we're doing is putting all of these tools together, combining to be able to handle the algebra related to solving absolute values. Here's an example of why graphing is so fundamentally important. We have y equals absolute value of x minus 2. Which if I were to graph would be an absolute value curve that is shifted to the right 2. It's going to look something like this. And then we have the line y equals negative 2 plus a half x. That's a very gradually increasing line with a negative 2y intercept. Accurately drawing graph with a 4, 0 x-intercept is going to give us the impression, which I believe is true, that there is no solution to this equation. There is no value of x that will make the left and the right-hand sides the same. But what I decided to do here was to ask the question, even though I already know, I've spotted that there's no solution, what does the algebra tell me should happen? So again, the algebra says to get rid of absolute values, we need to break into two equations, one where we leave the equation alone without absolute values, and the other where we take the opposite of whatever's in the absolute values. We do our algebra, and here we get x equals 0. I can see that when x equals 0, if I were to extend this absolute value graph into the negative realm, I would intersect the blue line when x equals 0. We can see as well, if I solve the other equation, I multiply by 2 to fraction bust and get x equals 8/3, that if x were equal to 8/3, that would be my other intersection, which again is not part of the absolute value. So watch what happens when I try to check. When I put in 0 for x into my original equation, I get x, or positive 2 on one side and negative 2 on the other. We can see that here. Here's the negative 2 for y, and here's the positive 2 for y. So they're a mirror image of each other, rather opposites of one another, which are not equal. So we can see that that was a lie. I knew it was a lie before I ever got through it, but I wanted to show you how the mathematics lies to you. It ignores negativity, basically. Substituting 8/3 in for x as well produces the y value on the left of 1/3 and negative 1/3 on the right-hand side. So once again, we can see these are not equal. And here again, the right-hand side produces negative 1/3 and the left-hand side produces positive 1/3. Opposites are not equals, and therefore we can rule out all these solutions. Now, the point that I wanted to make is, in practice, a good student would be able to look at this equation, perceive these two function graphs, and right out of the gate know that this is a fool's errand. There is no solution. So, anyway, the rest of this math here, if you finish the test in time and you have some time to kill, you can show me that the algebra lies to you. But for the most part, if you graph and you see that there is no solution, you can actually stop here with the two different equations and then just write lies underneath, and I'll believe you. So, thanks for watching. Have a good day.